Hey folks, in this section we're going to do some work with some new identities. They're called the Sum and Difference Identities. Here's what they are. These are the identities that I expect you to know. You really need to commit these to memory. First one says if you have the cosine of an A plus B, A and B, think of A and B being two angles, cosine of A plus B, the identity for that is it's equal to the cosine of A times the cosine B minus sine A times sine B. Likewise, if it's the cosine of an A minus B, you can rewrite that as cosine A cosine B plus sine A sine B. For the sine of A plus B, the identity for it is sine A cosine B plus cosine A sine B, whereas if it's the sine of A minus B, you rewrite that as sine A cosine B minus cosine A sine B. So why don't we look at an example of how we can use these identities. Alright, for the first example I thought we'd look at, you're asked to, let's say we're asked to find the exact value of the cosine of 2 pi over 3 plus pi over 4. So that's one of those identities that I just had up on the board. This is the cosine of A plus B. So according to the identity, I can rewrite this as the cosine of 2 pi over 3, cosine of A, times the cosine of pi over 4, that's like the B, minus sine 2 pi over 3 times the sine of pi over 4. Okay, now we just do it. We use our knowledge of the unit circle that we know the cosine of 2 pi over 3. Cosine of 2 pi over 3, we know that is negative 1/2. We know the cosine of pi over 4 is square root 2 over 2 minus the sine of 2 pi over 3. Well, we know that's square root 3 over 2. And then the sine of pi over 4 is the square root of 2 over 2. So just to clean this up, if we take negative 1/2 times square root 2 over 2, we'd get negative square root 2 over 4. Remember, numerator times numerator over denominator times denominator. Gives me that. Minus square root 3 times square root 2, that's square root 6 over 2 times 2, which is 4. Hey, check it out. Since our fractions already have a common denominator, it's really no extra work to just make this one fraction. Negative square root 2 minus square root 6 over 4. And that would be the exact value of cosine of 2 pi over 3 plus pi over 4. Let's look at this one. Well, this part B. The sine of 2 pi over 3 plus pi over 4. Okay, well, here it is. It's a sine of an A plus B, so we need to remember the identity for that. So we use the identity. We rewrite this as the sine of 2 pi over 3, it's the sine of A, times the cosine of pi over 4, plus the cosine of 2 pi over 3 times the sine of pi over 4. So that's using the identity sine of A plus B. I used the identity to rewrite it. Now we just do it. Use your knowledge of the unit circle. You know the sine of 2 pi over 3. Well, that's square root 3 over 2. Cosine of pi over 4 is the square root 2 over 2. Cosine of 2 pi over 3 is negative 1/2. And the sine of pi over 4 is square root 2 over 2. And then just like I did up here in part A, multiply these fractions together and we get square root 6 over 4. That would be minus square root 2 over 4. Negative times positive would turn that into minus. And just like I did up in part A, set a common denominator so it takes no extra work really to make this one fraction. And so that would be square root 6 minus square root 2 all over 4 that is the exact value of the sine of 2 pi over 3 plus pi over 4. And that's it for that example. And then we do another one here. Let's look at the exact value, finding the exact value of the sine of pi over 12. Sine of pi over 12. Well, when I see pi over 12, I'm kind of thinking, are there two of those special angles on the unit circle that when I add or subtract them, it would give me pi over 12? And the answer is yes. Pi over 12 is nothing more than pi over 3 minus pi over 4. I mean, if you do pi over 3 minus pi over 4, you're going to get pi over 12. That's 4 pi over 12 minus 3 pi over 12. That's pi over 12. But look at being able to rewrite pi over 12 as pi over 3 minus pi over 4. That now allows us to use our difference identity for the sine of a minus b. So our identity for the sine of a minus b tells us to rewrite this as the sine of pi over 3 times the cosine of pi over 4 minus the cosine of pi over 3 times the sine of pi over 4. And now, since these are friendly angles that we know off the unit circle, we can determine the exact value. The sine of pi over 3, we know that's square root 3 over 2. The cosine of pi over 4 is the square root 2 over 2. Cosine of pi over 3 is 1/2, and sine of pi over 4 is square root 2 over 2. And, if we go ahead and multiply these fractions together, square root 6 over 4 minus square root 2 over 4, and making it one fraction since we have a common denominator. That's the exact value for the sine of pi over 12. Let's do another one here. Let's say you're asked to do the cosine of 8 pi over 15 times the cosine of 2 pi over 15 minus the sine of 8 pi over 15 times the sine of 2 pi over 15. You're asked to get the exact value of that mess. It's like, well, first look, it reminds me of a sum identity for cosine. This looks exactly like cosine A, cosine B minus sine A, sine B. So cosine A, cosine B minus sine A, sine B. That was the identity for the cosine of A plus B. So all of this here is really the result of doing the cosine of 8 pi over 15 plus 2 pi over 15. Well, look at the identity. If you saw cosine of 8 pi over 15 plus 2 pi over 15, you would use that sum identity and rewrite it like this. So I can use that identity to put it back together. I can add these two together, 8 pi over 15 plus 2 pi over 15. That's 10 pi over 15. And look at 10 pi over 15. That reduces down. 10 pi over 15 reduces down to 2 pi over 3, and that's something that we know off the unit circle. We know the cosine of 2 pi over 3 is negative 1/2. So the exact value of this mess was found by using an identity, the sum identity, and we determined the exact value of this mess is negative 1/2. So that's it for that example. Alright folks, in this example, let's say we're told angle A is living in quadrant 4, angle B is in quadrant 3. We're also given that the cosine of A is 4/7 and the sine of B is negative 8/13, and we're asked to find the exact value of cosine A plus B. Well, we know that cosine of A plus B, we know the identity for that. That's cosine of A times cosine of B minus the sine of A times the sine of B. We are given what the cosine of A is. We know the cosine of A. We were given that. It's 4/7. We're also given the sine of B. Here. We're given the sine of B is negative 8/13. So at this point in time, we know cosine of A is 4/7. We know the sine of B is negative 8/13. What we don't know is what the cosine of B is, and we don't know what the sine of A is. We can determine what the cosine of B is, and we can determine what the sine of A is by using our Pythagorean identity, by using cosine squared plus sine squared is equal to 1. And that's what I'm going to do here. I'm going to use that Pythagorean identity to get the cosine of B and also to get the sine of A. So let's get the cosine of B first. So over here to the side, to get the cosine of B, I'm going to put a little break here. I'm going to use the Pythagorean identity that cosine squared B plus sine squared B is equal to 1. We know sine of B is negative 8/13, so I'm going to substitute that in for sine of B. So we have cosine squared B plus a negative 8/13 squared equals 1. Now let's see, negative 8/13 squared, that's 64 over 169. Subtract 64 over 169 from both sides of the equation. So 64 over 169 subtracted from 1. And boy, what does that give me? Like a 105 over 169. I don't like fractions. Take the square root of both sides, and I get cosine of B equals plus or minus the square root of 105 over 13. Which will I use for this problem? Will I use the positive square root 105 over 13 or the negative square root 105 over 13? Well, since B is in quadrant 3, I know in quadrant 3 only tangent and cotangent are positive. I know sine and cosine are negative. So for this problem, since B is in quadrant 3, I am going to use the cosine of B is the negative square root 5 over 13. All right, so let's do a progress check. We know cosine of A is 4/7. We now know cosine of B is negative square root 105 over 13. We still need to get the sine of A. So let's come over here to find the sine of A. I'm going to use the Pythagorean identity. Cosine squared A plus sine squared A equals 1. Since I know cosine A is 4/7, I can substitute that in here to get 4/7 quantity squared plus sine squared A equals 1. Let's see, 4/7 squared, that's 16 over 49. Subtract 16 over 49 from both sides of the equation, and we get sine squared A is equal to 33 over 49. Take the square root of both sides, and we get sine of A is plus or minus the square root of 33 over 7. But for this problem, which one am I going to use, the positive or the negative? Well, A's in quadrant 4. In quadrant 4, I know the cosine is positive, but sine is negative. So for this problem, I'm going to use the sine of A is the negative square root 33 over 7. All right, so to find the exact value of cosine A plus B, I think we know all of these pieces and parts. We can now do the problem. Cosine of A is 4/7. Cosine of B, that's that mess, negative square root 105 over 13, minus sine of A. Well, here's sine of A, negative square root 33 over 7 times sine of B. Sine of B was negative 8 over 13. If we multiply these fractions together, we get negative 4 times the square root 105 over, let's see, 7 times 13. Is that like 91? Yep. Negative times negative is positive, so I have minus a positive, so minus 8 times square root 33 over 91. And of course, since I have a common denominator, I can make one happy fraction out of this, if I so desired, and say that is the exact value for, given this information for this problem, that's the exact value of cosine A plus B. And that is quite a mess. That's it for this problem. Hey, let's check out this example. Looks like this one's going to be a little bit more involved. Here we're given the tangent of A is 5/7 and cosine A is negative. Given the secant B is negative 4/3 and cosecant B is positive. We're asked to find the exact value of cosine A plus B. Here's where I'd start. I'd write down my identity for the cosine of A plus B. We know that's cosine A times cosine B minus sine A times sine B. So we have to determine the value of cosine A, cosine B, sine A, and sine B. And look at the mess we are given. First thing I notice, I'm given the secant of B is negative 4/3. Well, that tells me that cosine of B, it must be negative 3/4. Remember, reciprocal identity. So, we now know the cosine of B. Well, that wasn't too bad. But notice we still need to get the sine of B. That I used Pythagorean identity, cosine squared plus sine squared equals 1 to get the sine of B. So why don't we just do that right now? Let me put a little break right here. We're going to get the sine of B. So we're going to use cosine squared B plus sine squared B equals 1. Cosine is negative 3/4. Negative 3/4 squared is 9/16. Subtract 9/16 from both sides gives us sine squared B is equal to 7/16. Take the square root of both sides and we get the sine of B is plus or minus the square root 7/4. It's the same problem as before. Which one do I use for this problem? Do I use the positive or do I use the negative? Well, here's the key. We know cosine of B is negative 3/4, so that should tell us that angle B must be in quadrant 2 or quadrant 3, because cosine's positive in 1 and 4. Here's the other piece. Cosecant is positive. Well, what's the reciprocal of cosecant? It's sine. So if the cosecant's positive, its reciprocal, sine, must also be positive. So let's think about this. In what quadrant is cosine negative, sine positive? Well, that's quadrant 2. But the key, cosecant is positive means sine is positive. I guess we'll use the positive square root here because cosecant is positive. So let me make a note. Here we are going to use the sine of B is the positive square root 7/4. So we have a little check here. Ooh, we know sine of B. We know cosine B. We know sine B. We know nothing about A. We know nothing about the cosine of A or the sine of A. The only thing we know about A is the cosine of A is negative, and we know tangent is 5/7. If I know the tangent Seems like there's another Pythagorean identity. Let's analyze what's happening with angle A over here. I know that the Pythagorean identity, 1 plus tangent squared, is secant squared. I can now determine what secant is, which will tell me what cosine is, because secant and cosine are reciprocals. And then once I know cosine, I can use the other Pythagorean identity to get sine. So here, let's attack it. We know tangent is 5/7, so put 5/7 in for tangent. And let's see, 5/7 squared is 25 over 49. Add these fractions together, so 1 plus 25 over 49. That's 49 over 49 plus 25 over 49. So that should be 74 over 49 is secant squared. Take the square root of both sides, plus or minus the square root of 74 over 7 is secant A, which immediately tells me that plus or minus 7 over the square root of 74 is cosine A. And I initially saw cosine A is supposed to be less than 0, so cosine A is negative. So I will use cosine A is negative 7 over the square root of 74. Alright, so, little progress check. Let's see where we're at. We know cosine B, we know sine B, we now know cosine A. All that's left is to find sine of A. And to get the sine of A, I'm going to have to do some erasing here. So I better put in information that I already know before I erase and before I lose it. So here I go. I know cosine of A is negative 7 over square root 74. I know cosine of B is negative 3/4. That was the easy one. Minus, okay, I don't know the sine of A, so let me just write sine of A down here. Sine of B is square root 7 over 4. Okay, so now I need to get the sine of A. Let me find the sine of A right in this area. So let me erase this. And here I am. I'm going to find the sine of A. I'm going to use the Pythagorean identity. Cosine squared A plus sine squared A equals 1. We know what the cosine of A is, so we substitute that in. Negative 7 over the square root of 74 squared plus sine squared is 1. When I take negative 7 over square root 74 and square that, it gives me 49 over 74. Subtract 49 over 74 from both sides of the equation, and I get, oh boy, what is that, like a 25 over 74? That ended up being pretty friendly. Take the square root of both sides, and I get plus or minus 5 over the square root of 74. Which one do I use here? Do I use the positive or do I use the negative? Well, let's look and try to figure out what quadrant angle A is in. When we have tangent of A as a positive 5/7, tangent is positive in quadrant 1 and quadrant 3. We also know cosine is negative. Cosine is negative in 2 and 3. Looks to me like angle A must be in quadrant 3, because that's where tangent's positive and cosine is negative. So since A is in quadrant 3, I know sine is negative. Sine is negative in quadrant 3. Well, now I know what to put in here the sine of A. So let me pull that mess up here, negative 5 over the square root of 74. And boy, this looks like a mess, but it's not going to be too bad. Negative times negative is positive, so we get a positive 21 over 4 square root 74. And then, up to my parenthesis there, minus, this product will be negative, so minus a negative is plus 5 square root 7 over 4 square root 74. And again, notice you have a common denominator, so you could make that one fraction. You could make it 21 plus 5 square root 7 over 4 square root 74. And given that mess, we have now determined the exact value of cosine A plus B. A little bit more involved, but hey, if you know your identities, not too bad. So that's it for that example. Hey folks, a couple more examples. Hey, before we do this example, you may have noticed I didn't write up on the board the identity for tangent A plus B or tangent of A minus B. You'll find those identities in the book. In the grand scheme of things, they're not nearly as important as the sum and difference identities for sine and cosine. I do expect you to know the sum and difference identities for sine and cosine. Truth be told, if you ever needed to get the exact value of tangent of A plus B, you could always use a quotient identity and rewrite tangent A plus B as sine A plus B over cosine A plus B. Which is why I said I need you to know those identities for the sum and difference identities for sine and cosine. All right, hey, let's look at this example. Find the exact value of the sine of the quantity inverse sine square root 2 over 2 plus inverse cosine square root 3 over 2. And I think where I would start here is noticing this is something friendly off the unit circle. Remember, inverse sine is ripping an angle off the right half of the unit circle. And I know inverse sine is square root 2 over 2. I know that is pi over 4. So inverse sine square root 2 over 2 is pi over 4. I notice that's a friendly angle off the unit circle. I know square root 3 over 2. I recognize that as being one of those important points on the unit circle. Inverse cosine is ripping an angle off the top half of the unit circle. So I know inverse cosine is square root 3 over 2. I know that angle is pi over 6. So since I know inverse sine is square root 2 over 2 is pi over 4, and I know inverse cosine square root 3 over 2 is pi over 6, I've turned this problem into the sine of pi over 4 plus pi over 6. The sine of A plus B, which we have an identity for that. We know we can rewrite this as the sine of pi over 4 times the cosine of pi over 6 plus the cosine of pi over 4 times the sine of pi over 6, which we can crank through this pretty quickly now. The sine of pi over 4, that's square root 2 over 2, whereas the cosine of pi over 6 is the square root 3 over 2. Cosine of pi over 4, square root 2 over 2, and the sine of pi over 6 is 1/2. Multiply these fractions together. Square root 6 over 4 plus square root 2 over 4, or as one fraction, square root 6 plus square root 2 over 4. And that's the exact value of that mess there. One more example, and it may not be quite as friendly as this, but the concept will be the same. All right, hey, here in this last example, we're asked to find the exact value of the sine of the quantity inverse sine 5/13 plus inverse cosine negative 12/13. A little bit more involved in the last example, and in the last example, I had stuff in here that, hey, I knew off the unit circle. Not the case here. But remember, please remember, this represents an angle off the right half of the unit circle. I don't know what that angle is, so let me call it something. Let me call it A. Let me write that over here. There is an angle A that is equal to the inverse sine of 5/13. And I know that inverse sine of 5/13, A equals inverse sine of 5/13. I know that that really means that the sine of A is 5/13. Likewise, I know this is an angle off the unit circle. Inverse cosine. Inverse cosine finds an angle on the top half of the unit circle. It's on the top half of the unit circle. I don't know what that angle is. Let me call it something. Let me call it B. So let me write that here. B is the inverse cosine of negative 12/13. But that really means the cosine of B is negative 12/13. I already have two very important pieces of information. Keep in mind, I know this is an angle and I'm calling it A. I know this is an angle and I'm calling it B. That's what I've written down here. By doing that, I've turned this problem into sine of A plus B. I called that angle, I called it A. I have it written over there. I called this angle B. I have it written over there. I know an identity for the sine of A plus B. I know it's the sine of A times cosine B plus cosine of A times sine of B. And I already know that the sine of A is 5/13. I know this. I know it's 5/13. I know cosine of B is negative 12/13. I know cosine B is negative 12/13. All that's left for me to do is to determine cosine of A and sine of B. And once again, I'm going to use Pythagorean identities to determine the exact value of cosine A and sine B. So let me make a little break here. Let me find the cosine of A in this area. So cosine squared A plus sine squared A is 1. Cosine squared A plus 5/13 squared is 1. Cosine squared A, let's see, 5/13 squared is 25 over 169. Subtract 25 over 169 from both sides. I get 144 over 169. And I have cosine of A is plus or minus 12/13. And we always have to figure out which one are we using, the positive or the negative. Well, this equation here, I know inverse sine is finding an angle off the right half of the unit circle. That puts me in quadrants 1 and 4. Sine is positive, I'm in quadrant 1. In quadrant 1, angle A is definitely in quadrant 1. And I know for any trig function, in quadrant 1 it will be positive. So for this problem, I will use the cosine of A is the positive 12/13. Check. Now I know the cosine of A. Let's get the exact value for sine of B. And I'll put that right here. And yes, I'm going to use the Pythagorean identity cosine squared B plus sine squared B is 1. I know cosine B is negative 12/13. So substitute that in. 12/13 squared is 144 over 169. Subtract 144 over 169 from both sides. Gives me sine squared B is 25 over 169. Take the square root of both sides and we get plus or minus 5/13. And yes, which do we use, the positive or the negative? Let's figure out where quadrant B, let's figure out in which quadrant angle B is living. This equation tells me B is in quadrants 1 or 2. It's the top half of the unit circle. Cosine's negative, got to be out in quadrant 2. In quadrant 2, sine is positive. So I'm going to use the sign of B is the positive 5/13. Check. I know all the pieces and parts now, so let's substitute in sine of A. Here it is, 5/13. Cosine of B, it's over there, negative 12/13. Cosine of A, 12/13. And the sine of B, 5/13. And we multiply this stuff together. We get negative 60 over 169 here. This gives us 60 over 169. And we add those together and we get 0. So it's like we just did a lot of work for nothing. And that's kind of neat that we ended up with 0. But it's the process of doing this problem. The first one I did that looked like this, the prior example, was much easier. This one was a little bit more involved, but it's nothing you can't do. It's bringing together stuff you already know. So that's it. Hope this example and these examples have made sense.